recording. So as always, if you speak, your voice is going to be on the recording, but, you know, it's no big deal. Well, it's no big deal for me, you know, but it's like, now I've got to find my pen. It'd be nice if I could find my pen. So there's that, and I've got to scribble, yes. So this is on the electric field notes. So the next 4 chapters are going to be on basically electric stuff, electric field, electric force, electric potential energy. We'll talk about uniform fields and non-uniform fields. We'll find that electric fields are incredibly useful. With gravity, we tend to talk about weight, which is, of course, the force. And we use the electric field, but sometimes when we use the gravitational field, and sometimes when we're using the gravitational field, we tend to think of it, it's little g, we tend to think of it as the acceleration due to gravity, which is not the way I'd like you to think about it. I'd like you to think about little g being basically 10 newtons per kilogram. For every kilogram, you get 10 newtons. And it points downwards, so it would be minus g. So we get that. Okay, so we didn't talk about gravitational fields all the time, but with electric fields, we'll talk much more about electric fields rather than electric forces. But we get there through electric forces. There's going to be 4 or 6 equations that are all very similar, and the trick is you write them down side by side so you don't get them confused. So we'll go through that, and I'll guide you through that. The other thing, so people get confused about the equations, then the other thing that people get confused about is if they're in a uniform field, which would be like in a capacitor, or gravitationally near the surface of the Earth. Or are we in a non-uniform field, which would be like being around point charges, which would be like being sufficiently far away from the Earth that Earth was like in a direction, not just below us. It would be over there, and the moon would be over some other place. So it's like, you know, here's the Earth, and here's the moon. And if we're here, then there's some pulling force from the Earth, and there's some pulling force from the moon. So that gives us a more complicated situation than if we're just near the surface of the Earth, because then it's always uniform, and, you know, the pull of the Earth is always downwards. So electronically, we have to distinguish between a capacitor, where the electric field is nice and uniform, rather like near the surface of the Earth, and having point charges, plus Coulomb, minus Coulomb, and here's my point of interest, you know. So we're going to do that. We didn't do much interplanetary journeys in gravity, and it's a bit of a sadness, because if we'd done more of that, we would have been actually better set up for the electricity. And the argument is they've got enough to dealing with just the, you know, uniform gravitational field. You can bring in the more complicated stuff later. So, as we said last time, I think I'm right on this. As we said last time, we said the charges come in 2 flavors, positive and negative, and opposites attract, similar ones repel, and good old Millikan did his experiment where he drove these particles down using electric field. He let them fall. Terminal velocity was pretty low. Drove them up sometimes, looked at all this motional behavior, and was able to work out the charge on the oil droplet. And he did not get 1.6 times 10 to the minus 19. He got some multiple of 1.6 times 10 to the minus 19. And because he did like 100 particles, he was eventually able to see that the smallest change was 1.6 times 10 to the minus 19. And he said, well, that must be the unit. That must be the quantization. That is the building block of charge, negative charge. And so, you know, every kind of student learns 1.6 times 10 to the minus 19 is the charge of an electron. It's very small. It's nice.
I thought electrons have a negative charge.
Yes, they do.
So Coulomb is a negative unit?
No, it's like, you know, I can go down a hill and it'd be a negative distance, but it doesn't mean to say that distance is negative.
Okay.
It's just an example of an amount of charge. The Coulomb is a magnitude.
Right.
So, and I think I said last time, the thing that, as I've got older, astounds me is that the proton, which is an up quark, and a down quark, is a completely different animal from an electron, and yet they have exactly the same charge. It's just like, hold on. It's like saying, my countertop is exactly the same height as my TV set. Oh, yeah, they're somehow balancing each other. Yeah, comment or question.
What's an above and a down? What's an electron?
Pardon?
What's an electron? It's a
It's a elementary particle.
No.
It's a lepton.
so it's its own.
It's its own thing.
But
We can't find anything that's less than an electron.
Okay.
Let's get to. I'm sure some people can. Theoreticians have sort of their theories, but it's not in the. It's not proven, and it's not. It's not in my dictionary yet. Let's put it that way. Man, I'm not sure about recording these things. So, did I show you this video?
Yeah.
Then we won't see it because it's going to be the same this time. We talked about smearing charges on top of insulators, and how in some ways it's great because we can do photocopying, and now in other ways it's not very good because we don't know where the charge is, so we can't have a nice uniform, well-behaved experiment. And so with a lot of electrostatics, you'll find that we have a conductor which lets the charge spread out nice and uniformly, but we make it into an isolated conductor by sitting it on an insulator. So the charge is trapped within the conductor, but it's able to uniformly distribute itself, which is kind of nice. And then we started talking about this. This is really important. So along came Newton. And Newton said, well, hold on. We have an apple. There's the mass of the apple. And we have the earth. There's the mass of the earth. And as the apple gets bigger, I expect more gravity. And as the earth gets bigger, I expect more gravity. So put those guys on top. This is the weight. And the separation, well, if the apple was in space, not that he knew much about space, but if the apple was in space, as the distance gets bigger, you expect the pull to get less. And you can get that, again, I think as he did, from just using hard logic, which is, if that's not the case, then an apple on the moon pulls me just as hard as an apple on the earth. And that's kind of like a bit hard to imagine. Or if it's even more extreme, if the pull of gravity increases with distance, then an apple on the moon will pull me harder than an apple on Earth. And then an apple on Pluto will pull me even harder, and an apple on that star will pull me even harder, and that's just not going to be the case. So the only logical thing is that as the separation increases, so the force of gravity decreases. And then he put his visualization. He was a good visualizer. He put his visualization hat on, and he said, we have this thing called gravity, and it starts off at this object, and the effect, the influence of this mass spreads out in all directions. In all directions. And it has to spread out over bigger and bigger spheres as its influence spreads out further and further. Same amount of stuff spreading out over a bigger and bigger sphere, well, its intensity falls off as the inverse of the area. If you've got twice as much area, you have half the intensity. If you have 3 times as much area, you have a third the intensity. It's the only way you can do it. You've got the same amount of stuff spreading out over a bigger area. Like paint. If you have twice as much area, the paint's half as thick. It's just the way it's going to be. So he said, well, this depends on 1 over the area. So the area goes as r squared, 4 pi r squared. So that should go as r squared. If it was cylindrical, if it was like a wire, say, and it was cylindrical, so it spread out over the radius of something, I'd expect an inverse relationship. But because it's spherically symmetrical, it was an inverse square relationship. And then he wanted to get to an equal sign, and so he put in a fudge constant. He had no idea what that number is, and it wasn't found out for probably over 100 years when Cavendish came along and did the experiment and found out what the number was. So you go from a proportionality sign to an equal sign using a fudge factor, some kind of constant of some kind. And this is called a gravitational constant. We know the value of it now. So that's the breakthrough kind of like thinking. It's largely theoretical, but it's visualization. That's how you make equations. That's how people make equations. They say, what does this thing depend on? And in your careers, you will make equations. It might not be as anything quite as important as this. It might be about just how your little widget that you just made works. You might have to do an equation for the inputs versus the output. But you'll be doing what Newton did. You'll be developing these equations. So recognizing how you know whether something goes on top or something goes on the bottom, or whether it's linear or squared or whatever, is good practice to have. We are talking about something that's magical. I mean, you have a black box machine where you don't really care what's on the inside. You don't want your customer to worry about how it works. You want your customers to know what you get out versus what you put in, because it's complicated. Well, isn't gravity just the same, isn't it? We don't really know how gravity works. All we know is the inputs and the outputs. The inputs are the masses, the outputs the force. I mean, we don't really know what's inside the gravity box. We just know that there's a thing called gravity. I mean, can you remember what does a particle physicist say causes gravity? Can you remember? Pardon? Yeah, it's the exchange of a particle. They have this wacky idea that there's like skateboarders going down the street, and one skateboarder throws a bag to another skateboarder, and that skateboarder goes off in that direction, and that skateboarder goes off in that direction. And they say, look, passing that bag causes a repulsive force. So they think of forces as being caused by the transition of particles from one object, transition of particles from one thing to another. And sometimes it causes repulsion, sometimes it causes attraction. But that's how particle physicists think about forces being created. So they think that the moon is full of these particles and the earth is full of these particles, and they keep going between the two of them, and as they keep causing between the two of them, then we get this attractive force. Do you believe it? It's like, until they have a bottle full of gravitons, it's a useful model.
So they're just holding on to that what they believe in, or?
I'm sure they do. I'm sure it's so they do and they don't. I mean models. My professor came in my junior year and said, you'd be amazed at how many people still believe in electrons. And I thought, being a pretty lousy student, I thought, did I miss something? When I arrived late, did he explain why there's no such thing as electrons, and I'm one of those people? And he was just trying to stir us up about, it's a useful model. Think of it as a particle, think of it as a fuzzy ball, it works. And the same goes for these things. Always take your models with a pinch of salt, because they may change, but rely on them, because they, to the extent that you're dealing with, they will tell you the future. It doesn't matter if they're right. And they do evolve over time. And as we get better at measuring, we need finer and finer measurements. The pull of gravity is not 9.8 meters per second squared, newtons per coulomb, newtons per kilogram, all over the Earth. If you fly over a bit of the Earth that's denser, you'll have a slightly bigger number, and a bit of the Earth that's less dense. So if you do it properly, you're going to put that density business in. And it's a better model, but we don't need it most of the time. I'm sorry you had your hand up, and I've been like...
I was wondering if they think it's particles that cause it, how they account for the loss of mass.
So not all particles need to have mass. Maybe I'm getting one from you and you're getting one from me. But it just seems weird that my glasses never run out of these particles, and because of this, they're attracted to the Earth. What would Einstein say? Einstein would say that space-time is warped. It's like... So, all right, so then Coulomb had it much easier. Coulomb goes, well, hold on, I want the... It goes, I'm going to have the force due to electrostatics, and, well, it's going to be one little charge and one big charge, and, it's probably spherically symmetrical, so we're going to have over r squared, and, we're going to put KE down. So, it's the same thing. The nice thing about physics and engineering is often you're studying the same thing over and over and over again. It's just the nature is made up of simple laws that repeat. And they give you this complex universe because of the different choices you get to make with simple laws. Okay, so don't get tied down by the by the symbols. I could have put down Q1 and Q2. I could have put down little q and big Q, QA and QB, QX and QY, Q alpha and Q beta if I want to sound more fancy. Don't get tied bound by the actual letter. Get to recognize the form. You know the type of music by the form. You don't listen to, I don't know, you don't listen to country and western and go, man, what kind of music is this? There's all these twanging guitars. It's a new genre. You go, no, it's country and western. I know it's country and western because you recognize the pattern. Same with this. You recognize the form. You might not know if it's where I'm talking about gravity or I'm talking about electrostatics if I use really weird symbols. But, I'm not going to use really weird symbols. So we can do stuff with this. And one little thing I think I told you about last time is that engineers tend to use that, the more fundamental form. They, in a way, don't honor Coulomb. And we kind of like hide the 4 pi epsilon naught. Epsilon naught is a fundamental constant. And so is pi, if you think. And so is 4. These are fundamental constants. Epsilon naught is called the permittivity of free space. It's all to do with electrostatics. There'll be the permeability of free space, which is mu naught, which is all about magnetism. So engineers tend to write down that F is equal to 1 over 4 pi epsilon naught, and then they'd go QA, QB over R squared. And if you look at old textbooks, sometimes they'll have that in there. Okay, so, it's okay. And then the other thing is, I prefer to use the absolute values and not worry about signs in my equation. I really do care about signs. The textbook says write down QA as a number, write down QB as a number. If you have a negative sign, then that is attraction, because opposites attract. And if you have a positive sign, then that's repulsion, because similar things repel. And that upsets me a little bit, because we've been just driving into everybody that positive means to the right and negative means to the left. So it's kind of mixing. I feel a bit regretful that they give this automatic way of not visualizing. And they have this another rule, a new rule for the sign now, that's special just for this case. Whereas I would sooner you just did a diagram and said, oh, look at that. That's positive, that's negative. I guess my force must be in that direction because that's attractive. And then you can figure out, if you want to put a sign on there, what sign it would be. So the book tends to, I think the book tends to codify things a little bit much. It's traditional. It tends to be that way. And so you've got to remember the nomenclature, It'll go F12. Is that the force caused by 1 on 2? Or is that the force on 1 caused by 2? You got to know what they mean by the shorthand. I don't need to know what they mean by the shorthand. I just need to have a decent diagram. And I don't have any shorthand. I can visualize it. And that's my prejudice. So, remember my prejudice. Okay, so then if I want to do... so did I do this example? Let's do it then. So I skipped a slide. So we're going to say, what is the magnitude experienced by a 3 coulomb positive charge? So we have plus 3, I put it in another little sphere, and a 12 coulomb positive charge, 12 plus, and then that is separated by 4 meters. So there's my visualization. Now I'm not quite finished. There's my force. It asks what is the magnitude of the force experienced by the 3 coulomb positive. So here's my force. It's on the 3 coulomb, and it's going in it's pointing towards, oh no. I'm glad we got an eraser here. Not that I ever need it, but what did I do wrong? 2 positives. There's my force. Now, I noticed that on a diagram. I'm not sure I would have noticed that if it had just been a negative or a positive in an equation. Okay, so what is that force? F is equal to, always write down your equation. And big G, big Q, little q is going to be 3. I don't worry about the signs. And that's going to be 12 over, what's the separation? 4 squared, which equals 36 over 16 G. So F is equal to, what's that going to be? 9 over 4? 2.25 G. Put it in parentheses, and what am I forgetting?
Whether or not it's
Newtons. Could be in some other weird unit. Physicists we put down, and engineers put down units. Frankly, on a test, that's as far as I'd like you to go. We could put down 2.25 times, what should we multiply it by?
9 by 9 by 10 to the 9, isn't it?
So this is, oh, I'm sorry. I'm sorry. Just, man, I am asleep at the wheel.
We knew you,
So let's, what did I do wrong?
You put the G into
You got to laugh, haven't you? Because otherwise you'd be crying. So that would be K. And then we say, well, okay, we don't want Coulomb's constant. What is Coulomb's constant?
9 by 10 to the 9.
Is it 9 times 10 to the 9?
Yeah.
Good man. Sure.
Yep. It says so. Yeah.
So then you'd say,
According to your notes, that's what it is.
well, we believe them. So that is equal to whatever that works out to be. It's going to be, I'm going to cheat a little bit and go, it's going to be about 2.1 times 10 to the 10, I think, newtons. Yeah, something like that, approximately. You can't use the approximate symbol, but I can. Okay. So not bad. What is the magnitude of the force experienced by the 12 Coulomb charge? Can you write it down for me?
2.1.
Whose law says that? Which number? It's going to be Newton's. First law is inertia, second law is MA, third law is action-reaction. So it's third law. And there's a bit of a hint, and there's not much space. I know, right, so put your head in the mind of a teacher. You know sometimes if you give a lot of space to something, people are much more likely, even though it's conceptual, to do a calculation. Because there's this space, and he must have left this space for some reason. So just don't get fooled by that. Well, of course, I'm an engineer, so I want to know directions to things. So let's do one that's in 3 dimensions. Yes?
So why was it the same force?
Because forces come in pairs, and they mediate between 2 objects. And so this force is here, there must be a force there. Remember, when the skateboarder throws the bag, the skateboarder goes off in that direction and the skateboarder goes off in that direction. Both of them feel an equal and opposite repulsion. So I pull on the earth every bit as much as the earth pulls on me. The only difference is if I jump off a building, the earth hurtles towards me just as I hurtle towards the earth. The problem is that the earth is so much more massive, the hurtling is unnoticeable, whereas with me, because I'm so light, you see me accelerate tremendously. So it's like, it looks like it's only happening to one thing, but it's happening to both things. And the force is equal and opposite. So, let's go a bit more serious here. So, I'm going to say I want to change this into a vector form, and you say, well, I want it to be a vector. How do I make F into a vector? I put a little arrow on top of it. That's kind of nice. And then, how do I make a magnitude? This is a magnitude. We just used it. How do I make the magnitude into a vector? I put a unit vector. This is a unit vector. It's, if you like, a pointing vector. It just gives you a direction. What's the magnitude? How big is a unit vector? That's what it's called, a unit vector. If it was not 1, it would change the magnitude on this side, magnitude on the right-hand side equals magnitude on the left-hand side. If it was not a unit vector, it would change the magnitude by a factor. If it was a vector that's 5 units long, it would change it by a factor of 5. If it was 10 units long, it would change it by a factor of 10. And that would change my numerical answer. So it's got to be a unit vector. So the most common mistake, and I remember doing that, going, man, my notes must be terrible. This was before they gave out notes. My notes must be terrible because why not just cancel that R with that squared? And it's like, because they're completely different animals. One of them is a vector and the other one is a magnitude. They're like different things. They're about the same thing. They're like, it's like saying, well, the seat of my car is just like a wheel. I'll just use my seat as the wheel. They're about the car, but they're not the same thing. Yeah.
Why isn't R measured as D or symbolized as D for distance? Why use R?
I don't know. I think to emphasize it is kind of radially about the mass, but I don't know. You've got to pick something, So yeah, good question. It would change things a little bit. It would make things maybe a bit simpler. Okay, so this is a unit vector. So it's R with a little hat on top. Little hats mean I'm a unit vector. Little arrows mean I'm a vector. And so Coulomb's constant is 9 times 10 to the 9, and Q is charged in coulombs, and R is in meters because we're using the SI system. And R hat is a unit vector, and it's best to consult the diagram, your diagram. So I'm going to tell you something like, oh yeah, charge A is at this point in space, and charge B is in that point in space. I suppose I could say that charge B is that vector away from charge A, but somehow I'm going to give you a geometry here, and then you're going to do the rest. So let's look at an example of that. And there was a joke. So teachers tend to, you have friends who are teachers, and there's jokes go around about teaching. Some of them are a bit mean, but some of them are like, just to let you know, there's a T-shirt you can get at certain teacher sites, and it says, it's on the syllabus. And teachers tend to show these to each other at the beginning of the semester because they get a lot of questions, and the answer is on the syllabus. And so it's like putting students down. I just went to a teacher training shop full of teachers. Okay, how many people do you think were on their cell phones during the presentation? About the same proportion as now. It's kind of like we are no better. We just are at the other side of the table, So there was this joke, and it showed basically the physics example used in class, and it was like 2 + 2 =, and then it had the physics example for homework, and it was 2 to the power 7 plus 2 to the power 4 equals, and then the physics question on the test, and it was 2 to the hieroglyphic, star, divided by an imaginary number equals. And it's like, and it's true. And it's kind of like the one I have to do is easy, and then the one that you have to do for homework is clearly harder, and the one that you have to do at the test is clearly harder. And so what's the justification? And the justification is that if I give you a hard one to begin with, and you don't follow it, you're lost. So the idea is I give you an easy one to begin with, and then we do step by step. It gets a little bit harder and a little bit harder. Now that means more homework questions. So for instance, in Physics 1, I have this homework that's like 50-odd questions long. And people go, that's too much. And I go, well, all right, I can give you just the last 5 questions, but you won't be able to do them. By having the little steps, you can make your way through it. But every now and then I like to give you a warning of what's coming. So this is one of those ways. This is one of the harder questions. So I just want to show you this is fair game, and it's a beautiful skill. So we say a positive through column charge is located at that. So I don't try to, although I'd love you to be able to draw your 3-dimensional drawings. Who cares? We just, that's what it looks like. And all I got to do, I'm thinking like symbolically plus 3. And this is going to be, I'm going to write it down at the side. So this is going to be 2i plus 3. So I'm not going to be good at writing sideways. Plus 4k. And this is going to be in meters because it's a displacement from the origin. And let's have a look. I have another one which is, I'm going to do that like that. And that's going to be a plus 12. And this is going to be a 3i plus 5j plus 1k. And I am, you know, I didn't put my little hats on, but I am keen to put my units down because that's what I will forget on a test, and that will eventually lose me points. So I'm not going to give points away for that. So I put my units down very, very, very often. I sometimes forget my little hats because, you know, it doesn't really matter. Now it says, what is the vector force experienced by the 3 Coulomb charge? So on your diagram, is it an attractive or repulsive force? So there's the force I'm interested in. Call it Fe. Now, I wonder if I can change. Oh, I can. This is going to be so cool. You're going to be so impressed by this because I've been practicing while you've been there, not there. Well, not practicing enough by the looks of things. But I want that. I want the colours. Where's the colours gone? There. Let's do it as a... Now I can't decide. This is a sad thing. Green. Okay. So the equation is Fe is equal to Ke little q big Q over R squared times R hat. And well, I need to somehow codify this separation. I might have given you this separation. I might have said the vector going from the 12 to the 3 is, and just given you that. And who cares where it is with respect to the origin? But I'm doing the longer version here today. There's a little bit of vectors you need to know. So I want to somehow get the ijk for, let's call it R3. I'm going to call this bit R1 and this bit R2. I'm just making that up. I didn't practice that. I'm just making that up. It doesn't matter. And I look at my diagram, and I want to have a vector relationship linking R3, which I don't know, but R2, which I do know, and R1, which I do know. So if you were to look at my diagram, what vector equation would you write down? R1 equals R2 plus R3, or R1 plus R2 equals R3, or R1 equals R2 minus R3. Look at your diagram. It's a vector diagram. You know how to add things using vector diagrams. So what would you write down? Commit yourself to something. Write something down. So it's going to be... what's the process of addition? You put what of one vector on what of another vector. Yeah. So it's head to tail. So this is not addition because the two heads are together. And this is not addition because the two tails are together. So this is the process of addition, yeah? I added these two together. So I would say R2 added to R3 equals R1. Yeah? Just from my diagram. You might have drawn different letters. You might have a different diagram. But from my diagram, that equation is true. Agreed? That vector there added to, there's the arrowhead, added to that vector there gives a resultant which is that vector there. Yeah? So now I say, well, let's do this. This is ijk. And I like to put my little grid system up. And I want R2. So I just look at my diagram and I go, well, it's 3 I's and it's 5 J's and it's 1K. And then, according to my equation, I've got to add an R3. So here's my R3. And my R3, oh, sorry, no. I've skipped a step. An important step. I want R3. I want to find R3. So R3 is equal to R1 minus R2. Does that make sense? I'm just rearranging to isolate R3. So now I want to find R3. So let's get my eraser. I want to find R3. And for that, I want, oh man, I'm going to have to, life is just sometimes a bit slow. So I look at this and I want R1. So I'm going to go R1, and I look at my diagram, and I go R1 is 2I, 3J, 4K. And I want to subtract from the R2. So R2 is down here. I want to subtract it, so I'm just going to say, oh, well, let's put down the minus 3, the minus 5, and the minus 1. And that's minus R2. And then I'll add these guys together. So minus 1, minus 2, and minus 3. So I'm going to just double check this.
That's +3.
Plus 3, thank you. So let me just have a quick little thing here. So I want R2 minus R3 gives me that, yes. R2 minus, R2 plus R3 gives me that. So R3 equals R1 minus R2, that's right. I did R1, okay, so that looks okay to me. So this answer is going to be minus 1I minus 2J plus 3K meters. That is that guy. Okay? Yes?
If you didn't see the meters after the R1 and R2, you just know that it's the location and not the vector.
So the meters is just telling me what my units are.
Because if you want the distance between 2 points, you just P2 negative P1.
Is that right? Would you get the same IJK vector?
No.
Then it's the distance between these two is actually not given by the IJK, it's given by the magnitude of the IJK.
You're going to get the same answer either way.
So, but we want the vector.
So how we do know that the 2I plus 3J plus 4K is the vector and not the location?
Because I've just worked out what that guy is. That guy. Oh, you're talking about down here.
Yeah.
Oh, because it says it's at this point in space, and so.
We can know that it's the location and not the vector between the origin and the...
I mean, but it makes no sense unless you're starting from the origin. I suppose I'm not writing. I mean, I think that's. I mean, yes, I did not say it was at the origin, but where else would I pick? And you couldn't do it.
It's the point. It's not. We only want to see the point, and not the. Like 3 and 12 are points, and not vectors.
So what you're saying is you've got a quicker way of doing it.
No, she's asking this, those are points or vector. Like like the points in direction original problem. The first two are points.
Okay. So these are points, and they are defined by a vector from the origin. Okay? Yeah. And I want to find this vector. I want to find this vector for various reasons. Okay? So this is how I'm going to find this vector. So if you have a quick way of doing it that works, then go for it.
Okay, I just want to know if the given numbers are vectors and not location.
If the given numbers, they are a location which I'm defining by a vector.
So it's vectors.
Yeah, I think there's a vector. I mean a vector. I've got people putting their hands up, so I've got a whole bunch of comments. And I presume you're trying to help me rather than sink me. so I don't know who's getting you first. Oh, so then, yeah.
The vector can, I mean, it's referring to, you can find the point from the vector, but you need those vectors to find the vector between the 2 points.
I want the vector
that's-
between the 2 points, yeah.
So you use the vectors to find that other vector.
And
That vector does define points, but you need those vectors to find the other vector.
Well, you can find the vector if you have 2 points.
So,
But it's like the same.
Position of those points.
so, as long as you can find me that R3, I'm happy. Okay? Okay? And you get the same answer I get, I'm happy, yes.
Pick the direction of the R3 because of the direction of the F
Yes.
diagram, right?
So yes, I'm being kind of. I think I'm a bit clever here. I am pointing my displacement vector from the 12 to the 3 because that's the direction of my force points. So why make things complicated for myself? Question or comment?
I mean, we actually don't even need if we don't have the origin, even if the vectors aren't for whatever reason in terms of the origin of the graph, it won't matter because when you're minusing it, it's not a relationship between the origin, it's a relationship between
Yeah.
the 2 vectors.
Yeah.
Well, you have
So let's move on. Because you guys are thinking more mathematically than I am, I suppose. So I want this vector, and I found this vector, so I'm happy. Okay. Now, what do I do now?
Divided by its magnitude.
No, I change the color of my pen. I do the more important thing, which for some reason, see, now my pen's given up on me. Man, this is a bad day. So why is my pen not enabling? Oh, there you go. So then I'm going to go along here to pointer options and then ink color, and I'm going to have blue. Okay. So now I want to write this out longhand. So I'm going to say FE is equal to KE. And what was my little charge? My little charge is 3. Again, I don't worry about the sign of it. The big charge is 12. Don't worry about the sign of it. Now, I want the separation between these two, which is the magnitude of R3. And the magnitude of R3 I get using good old Pythagoras. So it's going to be minus 1 squared added to minus 2 squared added to plus 3 squared. So that's my magnitude, agreed? And according to this, I've got to square that. That's what people tend to forget. So I'm going to square that. Okay, that's my magnitude. But now I want to find my unit vector. Well, this unit vector, this R3 points in the right direction. So let's just use that to begin with. So that's going to be minus 1i minus 2j plus 3k. So that's my unit vector. Unfortunately, it's too long. I want to normalize it. So, and the way I normalize it, I divide it by its own magnitude. So I go, oh, we want to divide by minus 1 squared plus minus 3 squared plus, no, minus 2 squared plus 3 squared. And I could, in the question, I would say, write me an expression for, and this would be an acceptable expression. I would put this in newtons. Now, because my unit vector is in the same direction as the force that I want, I just leave the signs alone. If by chance I had used this displacement vector, but I'd asked you about the force on the 12, and I realized that, oh man, he wants the force on the 12, I could have just put a negative sign somewhere or changed these positives to negatives. So I get my sign leaving alone or changing depending upon my diagram. If this drives you crazy, then by all means go 36 KE over, that's going to be 1 plus 9, 1 plus 4 plus 9 is going to be what, 14? And it's going to be square root of 14 squared, so that's going to be 14. And then you can go minus 1i minus 2j plus 3k over the square root of 14. And that's newtons. And that tells me the reason why I'm keen on this, rather than having you work out the number, the ijk, 0.72i minus 0.36j plus 0.78k, is if you make a mistake or you round, I can't tell what you did. But on this, I can, as I grade it, I can go through and I can basically say, I can turn around and say, okay, does that bit make sense? Yes. Do they know what they're doing as far as doing the magnitude? Yes. Did they remember to square it? Yes. Have they got the right signs? And then did they remember how to do this? So I can check it off bit by bit, and I can diagnose very easily if you've got this skill. You could make a math mistake getting the final vector, and yeah, that is something I'd rather you didn't do. But this is much easier for me to grade and find out, do you know what you're doing, rather than having that also be part of the question. So it would say, write an expression for, and it means you can leave it like this. I want you to leave it like that. Okay?
Do we need to remember what K is for the test?
You can leave it like this. So yeah, I don't need you to know what K is for the test. Okay. Cool? Something like that is going to be on there. I might forget all this and just tell you that. I might jump in there. I won't give you the diagram, but I might tell you the displacement vector from the 12 coulomb charge to the 3 coulomb charge is that vector. What is the vector force felt by, in this case, the 3 coulomb charge? So you jump in. You don't have to do this bit. This bit's just checking to see, are you comfortable using vectors? So you were first.
Since we're not actually drawing three-dimensionally, if our R2 and R1 are switched,
You still get the same answer.
our unit vector will be in the opposite direction.
Only if you chose to write down the vector in the opposite direction. I mean, what you're saying is if you name them differently.
No, if instead of having if in your diagram, if you switch the +3 coulomb with the +12 coulomb.
Oh yes, sorry. Okay, yeah.
And the unit vector would be different as long as our diagram justifies.
Yes, I look at your diagram and I look at the effects. Having defined a displacement vector, I've defined a geometry. So you should end up with the same vector. So if your ijk, if your unit vector is the opposite sense, you would need a negative sign in front. Because this is defined in space. This force is defined in space. It's got a certain ijk direction. And if you happen to have a different unit vector, if that is different, you have to accommodate it by having a negative sign there.
Right, but the way that the diagram's drawn right now, you could have a unit vector going in the opposite direction if the 12 and 3 are in reverse positions.
So you can choose to have the unit vector pointing in the downwards direction, in which case this force needs to have a negative sign somewhere in it to change that effect. Because this force is pointing upwards on this diagram.
Oh, so since it's pointing upward, it's positive?
No, I'm just saying this. I'm just using that as a direction. The question is, if we redefine things and we chose to have that unit vector in the opposite direction, would we get a different answer? And the answer is no. We'd have positive signs here, positive, positive, negative. So I'd need a negative somewhere else to make it into a negative, negative, positive. Because the direction is the direction in space. So you might look and you might say, oh look, this is in the opposite direction to my force. I need to put a negative in front, or I need to change whatever signs I have here to the opposite sign. So you've got to look at your diagram and you've got to analyze it, because you need to get the direction right, the signs right. Yes?
What was a comment and a question?
Yeah.
Just a comment about your thing. If you actually switch the two vectors, you will get different signs on the other one, but when you put the negative sign on it, it will just switch back to what you see there.
Yeah.
So that's
Yeah.
why at the end it will add up.
The answer is the
in
answer.
same direction.
Yeah.
You just have to be careful when you do your diagram to actually see that the FE arrow points in the same direction that your R3 arrow, or you put a negative sign so the arrow switches to the other side.
Yeah.
Same.
Alright.
Okay.
Unit vector and the vector.
Yeah,
Yep.
yeah, that's how I did it.
That's what I was thinking.
So-
My question was, in the case you don't give us the first two vectors and you just give us the last one, how will we know what the direction of the last one is without actually graphing?
I got to tell you,
Oh, you're gonna tell
the
them it's
vector,
same direction,
the
it's pointing
no,
towards-
I got to, I would, so let me go back. So what I would say in that case is, so what I'd say is you have a +3 and you have a +12. That blue pen doesn't work so well. And I would say something, language to the effect of, the displacement vector from the 12 to the 3 is such and such. What's the force felt by the 3, or what's the force felt by the 12? So I would have to define it that way. Yes.
Alright, I think I have a better way to explain my question.
Okay.
Right now, if my left hand is the positive 3 charge, and my right hand is the positive 12 charge.
I can't go back. It's all right, so we'll just talk me through it, and we'll just go through.
If my left hand's the 3 charge,
Okay?
my right hand is the 12 charge,
Yes?
then the force acting on this hand is going to be going this way, with a unit vector going that way. Correct?
The force on that is going to be pointing in that direction, and the unit vector of it,
Right, because this is how I've chosen to have my positive 3 charge, my positive 12 charge, and switches. Now, if I switch them, I'll have the exact opposite unit vector.
if you chose to.
Right, but force would still be positive
So we're talking about the force on what now?
on 3.
Now, so now you're doing the force down here.
Right.
So if you switch them and you choose to define your unit vector in that direction still,
No. The unit vector still.
then the signs on the unit vector match the signs on your force.
Right.
Because they're in the same direction. So if it's negative, negative, positive, if it's negative, negative, positive for that, it's negative, negative, positive for that. If it's positive, 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 it's positive, positive, positive. They're pointing in the same direction.
Right.
Yep. So your question at the end, so the question you should ask yourself at the end is, how does the direction of my unit vector that I chose match with the force that he's asking me about?
No, I think I get his question. His question is because now that you switch it, the direction is totally opposite, different to the first position, right? So, well, the thing is that you really
The
don't
unit-
know
the
where the
unit-
vector
That's
is
what
in
I'm
the
saying.
space, so it doesn't matter which one is in which side,
As long as
because at
it's-
the end the
You
numbers
look
will
at
be
your,
the same.
As
You-
long as it's the unit vector is either
You
that
look
or
at-
the opposite.
you look at your diagram. Yeah, you look at your diagram and say, what unit vector? So that's why I chose strategically to find the displacement vector in that direction, because my force was in that direction. By picking my R3 in that direction, or whatever it was called, I then have my unit vector in that direction. So I'm making life easy for myself. But I'm looking at my diagram all the time. Yeah, cool. So that, something like that, is going to be on the test. Okay, let's have a look. A point charge is located some distance from point charge, so point charge X, point charge Y. I left this little space to encourage you to draw a diagram. The point charge X experiences a force of 18 newtons towards. Okay, there's my force. And then I'd like you to answer these questions. So let's see if we can get this thing shown up. Let me just have a quick look and see how I'm doing for time on this. We've only got a couple more minutes, so let's do this real quick. Okay? So that means don't panic. So question 1, what can you conclude about the sign of the two charges? Click in. It's A is different, B is the same. I got 6 people. Come on. I got 8 people. Come on. 10 people. Come on. Come on. I'm going to end it now. So most people are saying A, and a couple of people are saying B, so let's just have a quick look at this. So, what can we conclude about the sign of the two charges? Well, it's an attractive force. It's pointing towards the other one, so it must be different, because opposites attract. Okay. What size of force is expected on Y? So, come on. So, what's the force? It's going to be attractive. I'll give you that much. It's going to be attractive. But how big is it? Come on. Come on. Come on. Yes. Okay, I'm going to stop there. So let's have a look at our graph. Our graph is, most people are saying B, which is 18. And in fact, that's true. It's equal and opposites. Yeah. Pardon? Some. Pardon? I know, there's always one. What direction will the force on charge Y point? Will it be towards? I'm not going to even do this. So which direction will it point? The way I drew it. So it will be towards X. And then what can you conclude about the magnitude of the two charges? Oh, I want this one. Bottom question. So what's it going to be? 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 What is it going to be? I got 16 answers. Come on. What is it going to be? I'm going to stop you there. Oh. Whoa. Does the Earth pull on the moon with the same force that the moon pulls on the Earth? Do I pull on the Earth with the same force that the Earth pulls on me? Am I the same mass as the Earth? Yeah, that one's... Oh, you can't write on it. It's going to be... You can't say anything. You don't know, you have no idea about those. They're not the same masses because they're the same gravity force. They're not the same masses, not the same charges because of the same other force. Same